In our previous session, we had discussed about the open and closed loop system. Now let us start off with the controllers and type of controllers. Controller. So basically, the concept of a control system is to sense the deviation of the output from the desired value and correct it till the desired output is achieved. The deviation of the actual output from its desired value is called the error. The measurement of error is possible because of the feedback. The feedback allows us to compare the actual output with its desired value to generate the error. The error is denoted as E of t. The desired value of the output is also called as reference input or a setback point. The error obtained is required to be analyzed to take a proper corrective action. The controller is an element which accepts the error in some form and decides the proper corrective action. The output of the controller is then applied to the process or final control element. This brings the output back to its desired set point. The controller is the heart of the control system. The accuracy of the entire system depends on how sensitive is the controller to the error detected and how it is manipulating such error. The classification of controller is based on the response of the controller and the mode of operation of the controller. For example, in the simple temperature control of a room, the heater is to be controlled. It should be switched on or off by the controller when the temperature crosses its set point. Such an operation of the controller is called discontinuous operations, and the mode of operation is called discontinuous mode of controller. But in some process control system, simple on-off decision is not sufficient. For example, the controlling the steam flow by opening and closing the valve. In such a smooth opening or closing of valve is necessary. The controller in this case is said to be operating in a continuous mode. Thus, the controller are basically classified as discontinuous controllers and continuous controllers. The discontinuous mode controllers are further classified as on-off controllers and multiposition controllers. The continuous mode controllers are further classified as proportional controllers, integral controllers, and derivative controllers. Some mode controllers can be combined to obtain composite controller mode, such as PI, that is proportional integral, PD, that is proportional derivative, PIT, that is proportional integral and derivative controllers. Most of the controllers are placed in the forward path of the control system, but in some cases, input to the controller is controlled through the feedback path. Let us start off with proportional controller. In this controller mode, the output of the controller is simply proportional to the error E of t. The relation between the error E of t and the controller output P is determined by constant and is called proportional gain constant, denoted by Kp. The output of the controller is a linear function of the error E of t. Thus, each value of the error has a unique value of the controller output. The range of the error, which covers 0% to 100% controller output, is called a proportional band. The block diagram from proportional controller is shown here. Though these exists linear relationship between the controller output and the error. For zero error, the controller output should not be zero, otherwise the process will come to halt. Hence, there exists some controller output P0 for the zero error. The characteristics are: when the error is zero, the controller output is equal to constant. If the error occurs, then for every 1% of error, the correction of Kp percentage is achieved. If error is positive, Kp percentage correction adds to the P0. If error is negative, Kp percentage correction gets subtracted from P0. The band of error exists for which the output of the controller is in between 0% to 100% without saturation. The gain Kp and the error band Pb are inversely proportional to each other, where Pb is equals to 100 by Kp. When the load changes, the output deviates from the set point, called as offset error. The major disadvantage of the proportional control mode is that it produces an offset error in the output. When the load changes, the output deviates from the set point. Such a deviation is called offset error or steady state error. The offset error depends upon the reaction rate of controller. Slow reaction rate produces small offset error, while fast reaction rate produces large offset error. Proportional controller is basically a feedback control and simplest form used in closed loop system. It provides faster response time, but as the system becomes complex, the response time difference gets accumulated, hence the response time becomes more faster. P proportional control linearly correlates the controller output to an error signal. a graphical representation of proportional controller for step increase in input at time is equals to 0. So the equation goes like P of t is equals to Kp E of t plus P naught, where Kp is the proportional gain constant and P naught is the controller output with zero error. The direct and reverse reaction is possible in the proportional control mode. The error may be positive or negative because error is R minus B and B can be less or greater than reference set point R. Advantage of proportional controller is that it reduces the steady state error and makes the system more stable. Slow response of the control system can be made faster by this controller. This advantage is that offsets are produced in the system and increases the maximum overshoot of the system. Integral controller is relatively a slow controller. It changes its output at a rate which is dependent on the integrating time constant until the error signal is cancelled. Compared to the proportional control, the integral control requires time to build up an appreciable output. However, it continues to act until the error signal disappears. This corrects the problem of the offset error in the proportional control. If the error is 0, the output remains at a fixed value equal to what it was when the error became 0. If the error is not 0, then the output begins to increase or decrease at the rate of ki percent per second for every positive plus or minus 1% of error. In such controller, the value of the controller output P of t is changed at the rate which is proportional to the actuating error signal E of t. It is represented as P of t is equals to Ki integral 0 to t E of t dt plus P naught. The constant Ki is also called as integral constant. Integrating the above equation, actual controller output is given. P naught is the controller output when the integral action starts, that is, at t is equals to 0. The output signal from the controller at any instant is the area under the actuating error signal curve up to the instant. If the value of the error is doubled, the value of P of t varies twice as fast, that is, rate of the controller output change also doubles. If the error is 0, the controller output is not changed. The control signal P of t can have non-zero values when the error signal E of t is 0. This is because the output depends on the history of the error, not on the instantaneous value of the error. This control system is used as an integral method to determine the response than using linear relationship, a graphical representation of integral control system for a step increase in input at t is equals to 0. Advantage is that due to ionic ability, it can return the controlled variable back to the exact set point following a disturbance, hence called as a reset controller. This advantage is due to slow response towards the error produced. It makes the system unstable. Derivative controller. It is a form of feed-forward control system. In this mode, the output of the controller depends on the time rate of change of actual error. Hence, it is also called as rate action mode or anticipatory action mode. The mathematical equation is given as P of t is equals to Kd det of dt. Kd is the derivative gain constant, and hence the block diagram of a derivative controller is also given here. Derivative gain constant indicates by how much percent the controller output must change for every percent per second rate of change of error. Generally, Kd is expressed in minutes. The important feature of this type of control mode is that for a given rate of change of error signal, there is a unique value of controller output. Let us look at some characteristics of a derivative controller. For a given rate of change of error signal, there is a unique value of controller output. When the error is 0, the controller output is 0. When the error is constant, that is when the rate of change of error is 0, the controller output is also 0 or constant. When the error is changing, the controller output changes by Kd percent for every 1% second rate of change of error. The advantage of derivative action is that it responds to the rate of change of error and can produce a significant correction before the magnitude of the actuating error becomes too large. It improves the transient response of the control system. Proportional integral controller. This is a composite control mode obtained by combining the proportional mode and the integral mode. The mathematical expression for such composite is given as P of t is equals to Ki integration 0 to t E of t of dt plus Kp E of t. Practically, Ki is indicated in terms of integral time Ti, where Ti is equals to 1 by Ki. Both Kp and Ti are adjustable. The Ki is also called as the reset rate. The change in Kp adjusts both proportional as well as integral part of the control system. When the error is 0, the controller output is fixed at the value that integral mode had when the error went to 0. This is nothing but P0. When the error is not 0, the proportional mode adds the correction while the integral term starts increasing or decreasing from its initial value depending upon reverse or direct action. It improves the steady state accuracy. It increases the rise time so response becomes slow. It decreases the bandwidth of the system. It filters out high frequency noise. It makes the response more oscillatory. Applications. The composite PI mode completely removes the offset problem of proportional mode. Such a mode can be used in system with a frequent or large load changes, but the process must have relatively slow change in the load to prevent the oscillation. Proportional derivative controller. It is a series of proportional and derivative controller mode which gives proportional plus derivative control mode. The mathematical expression for PD controller is given here. Pt is equals to Kp E of t plus Kd Kp det by dt. The block diagram for PD controller is also shown here. The Kd is called as the derivative time. Both Kp and Kd are adjustable. The derivative time Kd is the time interval by which the rate action advances the effect of proportional control. The various characteristics of PD mode are: it improves the damping and reduces the overshoot. It reduces the rise time and makes response faster. It makes the response stable very fast. It improves the bandwidth of the system. It cannot eliminate offset error. It may take the noise dominant at high frequency. It is not very effective for lightly damped system. Thus, overall, it improves the transient behavior of the system. The PD controller has disadvantage that it amplifies noise signal and may cause saturation effect in the actuator. Application. It cannot eliminate the offset error of proportional mode, but it can be used to handle a faster process load changes if offset error is tolerable. It is used in many industrial processes control system. Next is the proportional integral derivative control. It is the composite controller including the combination of a proportional integral and derivative control mode. It is called a PID control mode, and the controller is called 3-mode controller. It is very much complex to design but very powerful in action. It has advantage of all the mode. The integral mode eliminates the offset error of proportional mode. The response is very fast due to derivative mode, which is very sudden. It is used for any process conditioning. There is improvement in both transient and steady state response, but there is no offset, no oscillation with least settling time. PID controller, the mathematical equation for such a controller is given as Pt is equals to Kp E of t plus Kp Ki integration of 0 to t E of t dt plus Kp Kd det by dt plus P0. It is very complex to design but is very powerful in action. There is no offset, no oscillation with least settling time. There is improvement in both transient as well as steady state response. Graphical representation of PID controller output for step increase in input at a time t0 is given here. Advantage of PID controller. The integral mode eliminates the offset error of a proportional mode. The response is very fast and sudden response is due to the derivative mode. It can be used for any process condition. Effect of changing PID function. Controller. Proportional controller is easy to implement but is long settling time and has steady state error. Proportional derivative controller is easy to stabilize, has a faster response than just proportional controller but can amplify high frequency noise. Proportional integral has no steady state error but narrower range of stability. From this graph, we can see that the proportional and the proportional derivative controller produces the offset error. It requires significant time to attain the steady state. The proportional integral controller eliminates the offset but at an expense of higher maximum overshoot, a long period of oscillation and more settling time. The proportional derivative control produces the steady state very quickly with least oscillation and smallest maximum overshoot but offset is significant. The proportional integral and derivative control, there is no offset and the system achieves a steady state with less settling time. Thus, PID is the ultimate process composite controller. I hope you would have understood controllers and the type of controllers. Let us move on to a quadcopter example in the next session. Thank you.